The automatic door system of a lift uses a light beam and a photocell. An object entering the lift as the doors are closing blocks the light beam which is directed at a photocell. The drop in current through the photocell activates a relay which stops the doors from closing. A photocell works on the principle of the photoelectric effect. Photocells are also the basic units in the solar energy panels that convert some of the energy in sunlight into electrical energy. Solar energy panels are used to power pocket calculators and the Hubble Space Telescope. Photocells automatically turn on street lights at dusk. Photocell is also used in the mechanism to control the amount of light entering a camera. Introduction to concept of light quantization. In this lesson, you will learn to use the equation E equals hf for a photon, the meaning of work function and threshold frequency, to use Einstein's equation for photoelectric effect, hf equals W plus half mv maximum squared, the meaning of stopping potential, and to use E Vs equals half mv maximum squared. In 1901, Max Planck hypothesized that the energy radiated by a black body must be an integral multiple of a constant times the frequency. That is, energy is quantized. In 1905, Einstein extended this hypothesis to explain the photoelectric effect. Einstein proposed that energy of light is quantized and exists in discrete packets or quanta that are called photons. The energy of a photon is usually expressed in electron volts. Click on Definition and then on relationship between electron volts and joules. Calculate the energy of A photon of red light of frequency 4.30 times 10 to the power 14 Hz. B a photon of blue light of wavelength 476 nanometers. Then click each of them to get the solution. Summary. Energy of light is quantized and exists in discrete packets called photons. Energy of a photon of frequency f is hf. 1 electron volt equals 1.60 times 10 to the power minus 19 joules. Click the Label button to view the labeling for each object. Electrons are emitted from the surface of the cesium plate cathode of a photocell when blue light is incident on it. The emitted electrons, known as photoelectrons, are attracted to the anode, which is at a positive potential relative to the cathode. This flow of charge is known as the photoelectric current. Click on the cathode to observe the emission of photoelectrons. Drag the intensity slider to increase the intensity of the incident light. What change do you observe in the microammeter reading? Explain your answer. Answer: the microammeter reading increases. When the intensity of the incident light increases, the number of photons per second incident on the cathode increases. Subsequently, the rate of emission of photoelectrons increases. Thus, the photoelectric current increases. The relationship between the photoelectric current and the intensity of the incident light of a given frequency can be represented in a graph. Click the graph button. Monochromatic light of constant intensity is incident on a photocell. The frequency of the incident light can be changed by using light of different color. Click on each color block to change the frequency of the incident light and observe the changes in the microammeter reading. What are the colors of the incident light for which the microammeter shows zero reading? Answer: the colors are red and orange. A photoelectric current flows in the photocell when the frequency of the incident light is equal to or more than the frequency of yellow light. Will the microammeter reading show any changes when the intensity of the orange light is increased or decreased? Click on the orange light and drag the intensity slider. What do you conclude? Answer: the microammeter shows no reading. No electrons are emitted no matter what the intensity of the light is. Repeat the process with yellow light and light of higher frequency. When the frequency of light is equal to or above the frequency of the yellow light, electrons are emitted no matter how low the intensity of the incident light is. The minimum frequency of light for which photoelectric emission occurs is called the threshold frequency. If light with sufficient high frequency causes electrons to be emitted, the number of electrons emitted depends only on the intensity of the light or the number of incident photons. Free electrons in a metal are held by attractive forces. A minimum amount of energy is required to remove an electron from the surface of the metal. In case 1, why are there no electrons emitted when light is incident on the metal surface? Answer: there are no electrons emitted because the frequency of the light is below the threshold frequency. The energy of the photon is less than the minimum energy required to free a surface electron. Click the Case 2 button and then the Case 3 button to see photons of two different energies striking the metal surface. In Case 3, the emitted electrons possess a range of kinetic energies K, whereby the maximum kinetic energy is determined by the frequency of the incident photons. The minimum energy required to free an electron from the metal plate is equal to the energy of a photon with the threshold frequency. This is also the energy needed to free the least bound electron of the metal. This energy is called the work function of the metal. Click the relationship button to see how the threshold frequency is related to the work function. Summary. Photoelectric effect is the phenomenon in which electrons are emitted from a metal surface when the metal is illuminated with light. The number of electrons emitted depends only on the intensity of the light. The minimum frequency of light for which photoelectric emission occurs is called the threshold frequency. The work function of a metal is the minimum energy required to free an electron from the metal.